You have a function of two variables. And at some point, this function equals to 0. You are interested in the set in its zero-level curve. The theorem says that if the derivative of f in y at the point A is different from 0, then this set of x, y is given by y equal to function of x. If everything is analytic, then this function phi is analytic. Moreover, if we are not in the real plane, but in the complex plane, everything keeps the same. The set of zeros of the function f, the zero-level curve of the function f, is a graph of a function of y of x. So this is what I wanted to recall. Now, let us speak about classical results of generation of limit cycles. We have an equation df equals 0. Once again, in an elementary course of differential equations, it is said that the orbits, the phase curves of this equation are level curves of H. For instance, if H is, example, H is equal to y squared plus x cubed minus x squared, you will have the phase curves like this. The zero-level curve, at 0 you have a saddle, y squared minus x squared. Here you also have a minimal point of f. And you have level curves like this. The question is, if we slightly perturb this equation, what ovals will break and what one will survive? We can write a perturbation in the form df plus epsilon omega equals 0. Omega is a polynomial one form, a dx plus b dz dy, and a and b are polynomials. The question is, once again, what ovals will break and what one will keep closed slightly perturbed, but generate a limit cycle. When you perturb this picture, you may have, this is not necessary exactly this picture, but you may have this picture and all the ovals will break and only one, not necessarily only one, but in my example, one will preserve. The other ovals will be broken like this. So how to distinguish this oval? Do you understand the evolution of the pictures? Okay. How to distinguish this oval? The recipe was found by Pantriagin. It is very simple, like a student exercise. You have to combine a function I of t, which is an integral of the form omega over the oval gamma t. The oval gamma t is the oval, the component of the curve f equals to t. So if I of 0 equals if I of t0 equals 0, and the derivative of I is different from 0, then gamma t generates a limit cycle under this perturbation. So how to distinguish the yellow cycle? Take this integral, look whether it is 0, and then proceed. In order not to be to give my lectures purely in the survey form, I will prove this criterion for you with some technical detail missed. This technical detail is exactly the student exercise that I can recommend. So I now give the proof of the Pantriagin criterion. Consider the Poincaré map of the cycle. Let me restore that picture. This is my yellow cycle, gamma t0. And we consider the Poincaré map for this equation. Say the arrows go this way. All the orbits are closed. And we consider the equation df equals df plus epsilon omega equals 0. And this is the case epsilon equals 0. The Poincaré map depends on the point, say, z here. You may think about z as a real number, but at the same time, you may think that this is a complex picture. Switch your imagination. And this is a complex transversal line. So the Poincaré map, delta of z epsilon, depends not only on z, but on epsilon. For epsilon equal to 0, nothing interesting happens. What should I put here? Say it louder. Z. I come to the same spot. But when epsilon is non-zero, we have, I just decompose in epsilon this function of two variables. There will be epsilon times something plus O large of epsilon squared. The exercise that I miss, you definitely know that as this function is smooth in epsilon and z, there will be some function of z. The exercise that I miss is that here stands exactly I of z. Now I replace t by z, and let us think that we choose not the original coordinate of this cross section, but this z equals just to h restricted to this cross section gamma, f. So now we look for the fixed points. Fixed points of the Poincaré map correspond to the closed orbits. So we write down delta of z epsilon equals z. This z and this z are cancelled. We get that this part equals to 0. We can divide by epsilon and get an equation I of z plus O of epsilon equals 0. We know that I replace t by z, so now I write z0 instead of t0. I of z0 equals 0. I prime of z0 is different from 0. We are exactly in the setting of the implicit function theorem, and we can get an equation z is a function of epsilon such that delta of phi of epsilon equals to phi of epsilon. This is the initial condition for a limit cycle of this equation. Let us call it 1 of equation 1. So this is the description of the generation of limit cycles from the Hamiltonian vector field. Now, I will define you good limit cycles in the complex domain. We are still in the space of the coefficients. Here is an equation df equal to 0. I do not consider the whole neighborhood, but I just consider a one-dimensional family, exactly this one. And I make zoom. This is our family. This is the coordinate epsilon. This is epsilon equal to 0. Then we have a yellow oval of the Hamiltonian of the integrable equation. And for any, I will plot the figures in the phase space. This is the xy plane, and for this picture, for epsilon equals 0, we have the yellow cycle and all the nearby orbits closed. And for this value of epsilon, we have an actual limit cycle and these cycles are good. Good cycles. In C square, the yellow cycle will lie on a Riemann surface, and all the other nearby solutions are Riemann surfaces that wind towards this cylinder at least near this cycle. So these are good cycles as well. Let us turn back to our picture. I reproduce it. Here is our family. Cycles come to this neighborhood. The family, the path in the space of the coefficients crosses our cross section, and some limit cycles, complex limit cycles, come here. Is it correct or not that all these limit cycles may be described by the previous procedure? That is, are all the limit cycles of equation df plus epsilon omega equals 0, are all of them good? So, is it correct that you had a long and difficult travel, you changed your equation, your polynomial vector field, you brought it to this family, and is it correct that all the complex limit cycles that you brought here are good for the, in the sense that we discussed? So, without stating this explicitly, Petrovsky and Landis suggested that the answer is positive. And the main goal of my lecture today is to convince you that the answer is negative. The negative answer is not transformed to a strict theorem, but there is a theorem of Nikolai Dimitrov, my Cornell student of the 2000s, who very strongly supported the negative answer. So, we discussed good limit cycles. Let us now discuss bad limit cycles. I even have a temptation to give them Hispanic name, ciclos bandidos. First of all, I give you a model. Consider a non-autonomous equation with real time and complex phase space. So, z dot equals to lambda z, but dot is a derivative in the real time, and t is not in the real line, but in the real circle, that is in the real line factorized by 2 pi z. So the solution is simply z of t equals to exponential of lambda t times z of 0, and we have a very simple Poincaré map. This is the t circle, this is the z plane, and the point z, the Poincaré map, delta of, let us call this value zeta, delta of zeta is exponential 2 pi lambda zeta. So if lambda is not real, if lambda is not real, imaginary part of lambda is different from 0. Then the magnitude of this complex number is different from 1. If it is smaller than 1, then this is a linear contracting map. If it is greater than 1, then this is a linear expanding map. And the orbit of this map is either tending to 0 or tending to infinity. Yes? Thank you. Thank you. So the interesting case is when the imaginary part of lambda equals 0. Then the situation is the following. The magnitude of this number is 1. So it does not change the magnitude of z. So the orbit is a sequence of points on a real circle. So when lambda is when 2 pi lambda is irrational, what may be said about the orbit of this linear map? Yes? There are dents on any circle. Yes, yes. What if this is an irreducible fraction? What if 2 pi lambda is rational? Then what may be said about the orbit? What do you say? after n terms, let us call this for brevity nu. After n iterates, we will get multiplication by nu to the n, and nu to the n equals to 1. So the orbit will be finite. It will be a regular n, vertices of a regular n gone, and it will be a finite orbit. So we have this linear Poincaré map, and the orbit of the Poincaré map is finite, say a regular 6 gone, and the graph of the solution over the T circle will be like this. We make one turn and come to this point, a next turn and come to this point, the next one, and we come here, a next one, and we come here, a next one, and we come here. And then we come back. Probably 6 points was too much in order to plot this curve accurately, but I guess that you have an idea of this spiral winding over the circle and then coming into a closed curve, becoming a closed curve. So this is the image of the Bandido cycle. Ciclos bandidos, ciclo bandido. This is an image, an illustration let me show you, it was a model picture. Let me show you a realistic picture. What I will tell you, what happens? I will explain you now that ciclos bandidos occur in our situation. And after that, I will state the Nikolai Dimitrov theorem about rapid evolution of limit cycles. We are still considering our family of equations. We have this epsilon parameter curve. We have the Hamiltonian equation here. all the curves are closed. We have good cycles here. But it appears that for some sequence of values, or better to say even for some sequence of epsilon values, you have small neighborhoods in which the ciclos bandidos occur. So if this equation is from this neighborhood, then near to this good yellow cycle, a ciclobandido appears. It makes several turns and then closes. And it is located in a very small neighborhood of the good cycle. And the number of turns is growing up. So if this is an M turn ciclobandido, then closer to here, you will have once again an M turn ciclobandido, but in this sequence, M tends to infinity. It appears, let us, first of all, I made a statement without any explanation, but I hope that you have sort of a picture in your mind what stands behind this statement. Okay? And now I should claim the theorem of Dimitrov about rapid evolution. Before giving you a rigid statement, I would tell you the following. Ciclos bandidos are mysterious. We can observe them in a very narrow window to the parameter space, and we cannot say from where they come and where they go when the parameter tends to 0. So they are not good in a sense. And this is an important point, probably more important than the formal statement of the theorem. This is an effect. I have shown you the cycles that, not strictly proved, but very plausibly seem to be not good. And their evolution is rapid in the following sense. Look at the good cycle, yellow cycle. When epsilon tends to 0, it continuously evolves and sits on an oval of the Hamiltonian equation. And what does the bandit cycle? It quits not only the neighborhood of this good cycle, but a large domain in the phase space. I will describe this domain, and this will be a part of the statement of the theorem. And as epsilon is very close to 0, this evolution comes very rapidly. So now I describe the large domain that is definitely quit by the ciclo bandido when epsilon tends to 0. We take the map of C square to C just given by the Hamiltonian function f. We take the critical points Cj, where the differential of the function equals to 0. At these points, the implicit function theorem does not work, and the level curves may have singularities, level curves of f. Let us take the values of f at Cj. Cj are called critical points, and this is a universal mathematics terminology. And Bj are called critical values. So let us mark critical values here in the point C. Let us connect them with the infinity, and let us denote the complement to these rays by omega. Omega is the set of non-critical values cut along the rays going from critical values to infinity. They may be chosen in different ways. And let us take the inverse image of omega here. So this inverse image excludes all the leaves with singularities that pass through the critical values, and I cannot imagine that from any leaf there is a family of leaves corresponding to these values of the polynomial f that go to infinity. These leaves go to infinity. And you should delete all that. And what is remained is a complement to a codimension 1 surface. So sigma is an inverse image of omega, and the theorem of Dimitrov claims that the ciclos bandidos quit this large domain sigma as epsilon tends to 0. For some epsilon 0, we cannot extend these cycles in sigma. So we start here, say here, think that it is very close to 0, go to 0, and then come to a parameter value where you lose the ciclo bandido. That is, for this epsilon, the cycle was still inside this large domain. But for this epsilon, there is no continuous limit of the location of this cycle located that belongs to the large domain sigma. And what happens with this cycle afterwards as a function of a parameter is unknown. It is a good problem where these cycles go, but I have no answer to it. So this was the description of a picture. This is a description of how complicated the world of polynomial differential equations is, and my major goal today was to plot this picture for you. Do you have an idea of what is going on? Okay, in the remaining short time, I will give a brief description how the bandido cycles occur. This effect is called materialization of resonances. The name is due to Arnold, and he described this effect. But I am absolutely sure that Fatou already knew this effect. Remember that in the model example here, where was the model? Well, I will not look for it. In the model example for the Bandidos cycle, you had a linear equation with a linear Poincaré map. Now, suppose that you consider the Poincaré map of a good cycle. The good cycle evolves. We have a cross-section to a good cycle, and the intersection point of the cross-section with the good cycle also evolves. But we take a coordinate on the cross-section depending on the parameter so that it is 0 at the intersection point with the good cycle. Then the Poincaré map may be written in the form plus higher order terms. So suppose that lambda equals to exponential of 2pi phi, and phi equals to 1 over n. If the higher order terms will not be present, then you already know what is the behavior of this linear map. All the orbits of the points are periodic with what period? N, exactly, yes. Now, if the higher order terms are present, then for exactly this lambda, you will not see any periodic orbits at all. But if you have this map depending on lambda, and this is only the value of lambda at 0, then the following effect happens. In the linear case, as I said, for lambda equal to 0, all the orbits are periodic of the period n. In the nonlinear case, for epsilon equal to 0, they are all squeezed to only 1 0 point. But the theorem proved by a student of Arnold named Piartli, and I think that Fatou knew this theorem, in a generic family of the maps 2, this is my family 2. An n periodic orbit is born for small epsilon close to 0. I have only 2 minutes left, so I will not be able to show you anything like the proof, but I can show you something like the model. It appears that delta epsilon to the n for epsilon equal, no, I will not write it like this, equals to 1 plus delta times z plus, what is important, something like that. This delta depends on epsilon, and it is 0 when epsilon is 0. And we are solving the equation delta epsilon iterated n times of z equals z. The model is that we skip the higher order terms and z is cancelled, so we have delta z plus a z to the n plus 1 equals 0. Or z to the n, I divide by z, equals to negative delta over a. You see definitely n roots, n complex roots from this complex number. And this is exactly the periodic orbit that is born in the model case. So at this point, I will end. Thank you. Are there any questions, probably? Well.
Oh, okay.
Yes?
Can you repeat again how was this occurrence of this sequence of cycles bandidos here in this picture? In the five thank you. Number 5.
Would you like me to comment this picture?
Yes, please.
So these parameter values correspond to good cycles. Good cycles have the Poincaré map. Let me see, where is the formula for the Poincaré map? Here it is. And this lambda of epsilon tends to 1. As it tends to 1 in the complex plane, then there will be spots where it is exactly equal to a root of 1 of the degree n. Okay? If it tends to 1, then it will be sometimes this lambda. Laura, I do not see. Okay? Okay. And in the neighborhood of these parameter values, the materialization of resonances occurs and the periodic orbit appears. Okay?
Okay, thank you very much. Thank you.
Yes, please.
Thank you very much for your time, Professor. I just wanted to ask, do you have any literature for reference on the theorems you gave in today's lecture? For example, the last one?
There is a paper by Nikolai Dimitrov in discrete and continuous dynamical systems, somewhat around the year 10.
Okay, thank you very much.
Any other question? Well, I have one. Are those ciclos bandidos the same as the so-called alien cycles?
I do not think so. I do not know this term, alien cycles. I know that Jean Eccal uses the adjective alien, but in quite a different sense.
Okay. And do they have something to do with the multiplicity in the being zeros of this abelian integral I of z?
No, the good cycle near which a bandido cycle is born is of multiplicity 1, but its multiplicator or multiplier, the multiplier is this derivative at 0, this coefficient. Its multiplier is resonant. It's a root of unity of degree n.
Okay.
If this will be not a root of unity, but exactly unity, then the cycle will be multiple. But if it is simply a root of unity, then the cycle is robust, the cycle is persistent under the small perturbation. It evolves gradually when this epsilon changes and the multiplier changes. But bandido cycles are born near it.
Thank you very much. And any other question?
Well, I wanted to ask, because there are some cases, I think, Arnold mentions one in his Ordinary Differential Equations book, where you have two limit cycles, one which behaves as a repulsor cycle, and an inner attractor cycle around a singular point. And at some parameters, they clash and become one, he calls it degenerate cycle. Is there anything to say about the ciclos bandidos when you have the clash of two cycles in let's say, well, here it's the complex domain?
When you have a clash of two cycles, you obtain a multiple limit cycle, in the simplest case of multiplicity 2. And the corresponding Poincaré map is, this coefficient is 1, z plus coefficient and z squared. So this is a different situation. Materialization of resonances that I described here is of different nature, different behavior than splitting of a multiple limit cycle to several limit cycles. The similarity comes in the following situation. Let us iterate n times the Poincaré map of our good cycle. Instead of that, we can say, let us consider not our good cycle, but our good cycle run over n times. So, n-covered good cycle. And n-covered good cycle will become definitely simply a multiple limit cycle, because when you take this degree, this iterate of its Poincaré map, and epsilon equals to 0, you have exactly one here, and this is the definition of the multiple limit cycle. The linear term is z. So, though the materialization of resonances and splitting of multiple limit cycle are different things, yet there is a close relation between them. A good cycle itself is not multiple, but its n-cover is multiple. And for this, n cover of a limit cycle is splitting very good, and the Bandido limit cycle is born. But when epsilon changes, the good cycle, in a sense, remains the same. It evaluates smoothly. But the number of covers that you need to observe the materialization of resonances is changing, because phi is changing, n is changing, n tends to infinity. So near zero here, you have to make more and more covers over the good limit cycle. And this process has no limit.
I see. Thank you very much.
Thank you.
Any other question? ¿Más preguntas por ahí? ¿No?
Yes. What is a hyperbolic limit cycle in the complex domain? In the real domain, it is a cycle whose multiplier is different from 1. In the complex domain, a hyperbolic limit cycle is with multiplier different from 1 in magnitude. So this Bandido cycle for some parameter values may be hyperbolic and for some maybe not, but this is not important. I will say one word about the next lecture. In the next lecture, I will discuss effect of persistence. So something that happens in the parameter space when you continue some effect along a curve. But this will be persistence in a different context. So I wanted just to give a hint about how the next lecture will be related with the previous one. Well, thank you again.
Thank you.